Dear students, in the previous lecture, we have studied about enthalpies of different types of reactions, like enthalpy of combustion, enthalpy of atomization, the dissociation enthalpy, etc. Today, we will study about the lattice enthalpy of the ionic solids and how to calculate the lattice enthalpy or the lattice enthalpy of formation for the ionic solids. Lattice enthalpy. There are two definitions of lattice enthalpy. The lattice formation enthalpy. The enthalpy change when 1 mole of an ionic lattice is formed from its isolated gaseous ions. Example, sodium ion in the gaseous state plus the chloride ion in gaseous state gives sodium chloride crystal in the solid state. Lattice dissociation enthalpy. The enthalpy change when 1 mole of an ionic lattice dissociates into isolated gaseous ions. Example, sodium chloride crystal in the solid state dissociates into sodium ion in the gaseous state and the chloride ion in the gaseous state. The ionic solids are the crystalline solids with a long range order, and there is strong ionic bonds between the oppositely charged ions, that is cation and anion. Just because of the strong interionic bonding, the lattice enthalpy is very high. There is no direct method to calculate the lattice enthalpy, so we use the Born-Haber cycle. Born and Haber, they gave the Born-Haber cycle a very simplified but indirect method to find out the lattice enthalpy of the ionic solids. Let's see. The lattice formation enthalpy is highly exothermic. It is strongly exothermic because there are strong interionic bonds between the oppositely charged ions. And when the two oppositely charged ions make a bond, large amount of heat energy is released. Delta H is negative. Lattice dissociation enthalpy. It is an endothermic process because we have to give large amount of energy to break the bond between oppositely charged ions. The strength of the bond depends upon the charge density. Smaller is the ion, higher is the charge density, then stronger is the bond and higher is the lattice enthalpy. Let's see from the figure also. In the figure you can see that the size of the sodium ion is smaller than the size of the potassium ion, although both have +1 charge. Both are making a bond with the chloride ion. The size of the chloride ion is same for both. Since the size of the sodium ion is smaller, so it has higher charge density as compared to the potassium ion. Therefore, the bond between the sodium ion and the chloride ion is stronger as compared to the bond between the potassium ion and the chloride ion. The higher lattice enthalpy affects the melting point and the solubility. If the lattice enthalpy is high, then the melting point is also high because we need large amount of energy to dissociate the crystal, the ionic crystal into gaseous ions. Similarly, it affects the solubility also. If the lattice enthalpy is high, then the solubility of the ionic compound is low. Let me explain the lattice enthalpy for sodium chloride ion through Born-Haber cycle. Dear students, it is not a single step process. There are many steps which takes place while NaCl, the ionic crystal, is formed. Let us see. Dear students, let me explain you the lattice enthalpy of NaCl using Born-Haber cycle. Sodium, that is Na, is a metal. It is in the solid state. So I have to change it into the gaseous state. Chlorine is already in the gaseous state. Enthalpy of formation of NaCl, Na in the solid state plus half Cl2, that is in the gaseous state, gives NaCl in the solid state. Overall, it is an exothermic process. Now, there are many individual steps which takes place before the formation of NaCl. Enthalpy of sublimation of sodium. Since the sodium is in the solid state, it has to be converted into the gaseous state, that is enthalpy of sublimation. We have to give energy to convert a solid metal into the gaseous state. It is an endothermic process. Enthalpy of atomization of chlorine. Since chlorine is a diatomic molecule, so we have to break the chlorine molecule into chlorine atoms. Again, it is a endothermic process because we are breaking the bond between two chlorine atoms. Ionization enthalpy or ionization energy of sodium. In Unit 3 of class 11th, you have already studied about ionization enthalpy. It is the amount of energy required to remove the outermost electron from the neutral atom in the gaseous state. Sodium has one electron in its valence shell. We have to remove that. Now, the sodium is in the gaseous state. We have to give energy to remove that valence electron from the outermost shell against the nuclear charge. Therefore, again it is an endothermic process. Electron affinity of chlorine. Chlorine in the gaseous state plus one electron gives chloride ion in the gaseous state. Electron affinity is the amount of energy released when an extra electron is added in the valence shell. This is the step in which energy is released. Now, we have the sodium ion in the gaseous state and the chloride ion in the gaseous state. The both are oppositely charged ions. Sodium is a cation and chloride is an anion. Now, there will be a strong bond between these oppositely charged ions and NaCl will be formed. The sum total of all these energies will give the lattice enthalpy of sodium chloride. Now, let us see all these steps through the figure. The first step, that is the overall step, is Na solid plus half Cl2 gas to give NaCl solid. This is the required overall equation. Enthalpy of sublimation, that is conversion of sodium metal into sodium ion. Sodium in the solid state is converted to the gaseous sodium atom. This is an endothermic process and energy is needed to separate the atoms. Enthalpy of atomization of chlorine, half Cl2 in the gaseous state changes to chlorine atom in the gaseous state. We are breaking the covalent bond and it is an endothermic process. The first ionization energy of the sodium, because only one electron is to be removed. Sodium in the gaseous state gives one electron and it changes into sodium ion in the gaseous state. All the ionization energies are endothermic because the energy is required to overcome the attraction of the proton in the nucleus for the electron being removed. Electron affinity of chlorine. Chlorine in the gaseous state accepts one electron and it converts into chloride ion in the gaseous state. It is the exothermic process because energy is released as the nucleus attracts an electron to the outer shell of chlorine atom. The lattice enthalpy of sodium chloride, we used the Born-Haber cycle and calculated it indirectly by series of steps. Sodium ion in the gaseous state and the chloride ion is also in the gaseous state. Together, they form the sodium chloride crystal in the solid state. The bond between sodium ion and the chloride ion is very strong because the ions are oppositely charged. The overall enthalpy in this formation of crystal is exothermic. Calculating the lattice enthalpy by applying the Hess's law. The Hess's law states that the enthalpy change in a reaction remains same whether the reaction is carried out in one step or in the series of steps. The total enthalpy change of a reaction remains constant. Just by applying the Hess's law and by simple addition and subtraction of these enthalpies, we can calculate the overall enthalpy change of sodium chloride crystal, that is, the lattice enthalpy of formation of sodium chloride. Let's see this. 6 is equals to minus 5, minus 4, minus 3, minus 2, plus 1. The minus sign shows you are going in the opposite direction to the definition. The values are put up with the sign and the overall enthalpy is calculated as minus 776 kilojoules per mole. Or we can ignore the signs and just use the values. Like if we are going up in the figure, these values are to be added, and when we are coming down, these values are to be subtracted. Again, by this way also, the lattice enthalpy of formation of sodium chloride comes out to be minus 776 kilojoules per mole. In the same way, we can calculate the lattice enthalpy of magnesium chloride by using the series of steps. In the case of magnesium, again it is a metal, so we have to convert it into the gaseous state. In the valence shell of the magnesium, there are 2 electrons, so we have to give ionization energy twice because we have to remove 2 electrons and magnesium will convert into magnesium 2 plus ion. Whereas in the chloride ion, the chlorine already is in the gaseous state, we have to add 2 electrons which are lost by the magnesium ion, and the compound MgCl2 will be formed, and we can calculate the lattice enthalpy of magnesium chloride again by using the Born-Haber cycle. Dear students, today I explained you to find out the lattice enthalpy of the ionic solids using Born-Haber cycle, which is a very simplified but indirect method to calculate lattice enthalpy. The lattice enthalpy affects the melting point and solubility of an ionic solid. Lattice enthalpy depends upon the charge density. Smaller is the ion, higher is the charge density, stronger is the bond between the oppositely charged ions, and hence higher is the lattice enthalpy. And when lattice enthalpy is high, the melting point is high, but the solubility is low. In the next lecture, I will explain you about all those natural processes which have tendency to take place of their own or after proper initiation, and another important thermodynamic parameter, that is entropy. Thank you.